Look at this rocket shoving its way upward. The ripples distorting the sky are the physical weight of the atmosphere being shoved aside by thousands of tons of thrust. We rarely think of the sky as a physical substance, but planes, race cars, and birds all navigate a thick, heavy fluid. Every moving thing on Earth is engaged in a constant struggle against the pressures of our atmosphere. To move through this fluid, an object must balance four forces. Thrust must overcome the friction of drag to move forward, while lift must generate enough upward pressure to counteract the pull of weight. There are no exceptions to these physics. Achieving speed and sustained flight requires both engineers and biological evolution to find ways to manipulate these pressures. Fluid motion is defined by a struggle between two physical properties. There is viscosity, the internal stickiness and friction of the air, and inertia, the tendency of a moving object to keep traveling in a straight line. We calculate the winner of this struggle using the Reynolds number. It is a ratio of an object's momentum divided by the fluid's friction. This number determines exactly how the air will flow around a body. When an object is large and fast, the Reynolds number is high. Inertia dominates. The air cannot stay attached to the surface smoothly. Instead, it breaks apart into chaotic, swirling currents called turbulent flow. This is a profile of the classic silver racing car, number 12. At racing speeds, the air becomes a wall of turbulence, and a streamlined body is required to minimize the drag that tries to pull the vehicle backward. Engineers use large eddy simulations to visualize this chaos. They wrap a vehicle in a digital mesh of millions of cells to map exactly where the air begins to swirl. This data lets them tweak the surface curves and smooth the wake behind the car. If you scale down to microscopic sizes, the physics invert. At low Reynolds numbers, inertia essentially vanishes and viscosity dominates. To a tiny object, the air feels as thick and resistant as honey. Nature uses this resistance to its advantage. Pine trees equip their pollen with tiny air sacs that increase their drag. Because the air feels so viscous at this scale, the pollen can ride wind currents for miles rather than falling to the ground. While drag is about friction, lift is about circulation. Many believe a wing works because air travels a longer path over the top to meet the air on the bottom, but the true mechanism is dictated by the shape of the wing itself. This illustrates the CUDA condition. Air must leave the wing's sharp trailing edge smoothly, forcing a circulation pattern that generates lift. But if the wing's angle becomes too steep, the flow detaches, erupting into turbulence. Lift vanishes instantly. This is a stall. Here is a peregrine falcon during a slow landing approach. To maintain control at this steep angle without stalling, it relies on specialized feathers. It deploys a cluster of feathers called the alula on the front edge of its wing. These act as a small slot, funneling a high-speed jet of air over the top surface. This added energy forces the air to stay attached to the wing, preventing a stall even as the bird slows down. This photo shows a Boeing 747, which utilizes the exact same solution. Engineers installed mechanical leading-edge slats that function like the falcon's feathers. These slats ensure the wing generates enough lift to keep the massive aircraft stable and completely under control during steep takeoffs and landings. Generating lift is only useful if the vehicle remains stable. If an aircraft's balance is off, a single gust of wind can cause it to flip out of control. This diagram shows the balancing act required for static stability. Lift pulls upward at the aerodynamic center, while weight pulls down at the center of gravity. For the aircraft to be self-correcting, the center of gravity must be placed in front of the lift point. This front-heavy layout provides a natural safety measure. If wind pushes the nose up, the increased lift at the back of the wing creates a torque that pushes the nose back down, automatically returning the plane to level flight. These rules of stability govern almost everything that flies, until the speed of the object approaches the speed of sound. At high Mach numbers, the air no longer has time to move out of the way. Instead of flowing, the air is violently compressed. It stacks up against the leading edges of the aircraft, forming a rigid shock wave. This sudden change in air density completely alters the pressures across the wing. As the plane goes supersonic, the shock waves cause the aerodynamic center to shift backward. This moves the lift point away from the center of gravity, pulling the tail up and shoving the nose down. Pilots call this dangerous destabilization Mach tuck. To survive these shifting pressures, supersonic jets like the Concorde require a radically different profile. Its needle-like nose and swept wings are designed specifically to manage the shock waves that form when the air becomes compressible. Whether a wing is shaped by millions of years of evolution or decades of human engineering, both must solve the same equations of fluid motion. This albatross possesses long, narrow wings, a high aspect ratio design. This shape is a biological optimization that minimizes the drag created at the wingtips, allowing the bird to glide over the ocean with minimal energy. Modern designers use a mathematical tool called the adjoint method to achieve the same result. By calculating how every millimeter of a surface affects drag, they can mathematically evolve a wing or a car body until it reaches peak efficiency. These principles determine how a falcon hunts, how a city breathes, and how we cross the globe. Aerodynamics is the physical logic that dictates the shapes of the moving world. By understanding these rules of flow, lift, and drag, we can move through the atmosphere with the same calculated precision found in nature.